Alright, let us pick up where we left off in Chapter 1. We had just started talking about position versus time graphs and velocity versus time graphs. So this is a nice simple example. Take a second. If you can tell the story of it, tell yourself the story. Feel free to make it elaborate, some character development, a real arc. Make sure everybody, has some experience they learn from, grow from. But mostly this is just something traveling in a straight line, because that's where we're sticking with one-dimensional stuff, at a constant speed. And so we had said we could look at the slope of this, and the slope of this line was going to be our velocity. We cared if the slope was positive or negative, because then our velocity would have us going forwards or backwards. And we cared about its magnitude, its size, and that would be our speed. So let's leave this for 1 second, make sure we get some terminology that we're happy with. Specifically, that being speed and velocity. So speed is the rate of change of position. So I'm moving 4 meters every 2 seconds. If we wanted to write that out as an equation, I could say that my speed, which I still write as v because I want to confuse people, is 4 meters per 2 seconds, or 2 meters per second. Now, velocity is the speed in a given direction. So I'm moving 2 meters per second forward. We're going to differentiate this by drawing speed as just a plain old v, and velocity, a v with an arrow over its head, so that we know it is a vector. A vector, remember from last time, something has a magnitude and a direction. This is just a plain old scalar. A little dull, a little boring. So we could say 2 meters per second, specifically it is forward. And that forward is what gets us the vectory bit. Now, let's come back up here and ask, how could we get this from a graph? So I had said I moved 4 meters in 2 seconds, right? Now, I could find the slope of this line. I have a position and a time. This here is, x equals 4 meters. I'm going to call it x2 at t2, Judgment Day, equals 2 seconds. Here we have a position x1 equals 2 meters at t1 equals 1 second. Since this is a line, I can ask about the slope of it. Remember, slope looks like rise over run. Looking at this graph, my rise is going to be my change in x. My run is going to be my change in t. So this is going to look like delta x over delta t, or x2 minus x1 over t2 minus t1. This was 4 meters minus 2 meters over 2 seconds minus 1 second, which gives me 2 meters in 1 second. Nice thing to note, we didn't know we were starting out looking for a velocity, we just were looking for a slope. But it turns out this is positive, so that gets us our forward bit. And we have this nice meters per second stuff going on here, so we got the units already checking out for us. So that's kind of cool, right? Now, because of this, we can have one other thing that's kind of interesting. I can go back and now look at this and say v equals delta x over delta t. If I multiply both sides of this by delta t, I can see that, well, let's see, delta t over delta t is 1. V times delta t is, well, v times delta t. So we have v times delta t equals delta x. All right. So delta x, I don't need a new color for this, is equal to x minus x naught. This might be a little weird, but what this is really saying, when I say x, I'm saying x at time t. And when I say x at naught, I'm saying x at time 0, or at my original time. So I could say at some time t0. So original or initial time, final time. These correspond to my t's in here. All right, so now I could say, oh, also do be careful. These parentheses, these red ones, I think they're red, mean that we're looking at a function, x of t. These parentheses, the blue ones, are just plain old boring parentheses. Nothing fancy. So ultimately, I can say x, the position, as a function of time, looks like my initial position plus v delta t. So that's kind of cool. We will come back to this later, perhaps. For now, we want to just have this stored in the back of our head as a useful relationship. Later may mean homework, by the way. So this allows us to go from position to velocity. But now, a very clever person, or someone who has read ahead in the textbook, or is just really good at guessing, might wonder, is there some way to go from velocity to position? And the answer is that this area here is important to us. If I look at this area, I see that it looks like delta t times v. Now you may be thinking, wait, v times delta t, didn't we just see that appear a second ago? Like right here? And in fact, that is the idea that we're going for. This area is equal to delta x. So what this might mean, let's say that I'm traveling at 1 kilometer per hour, very leisurely, for, make it a little complicated, 2 hours. Question would then be, how far have I traveled? Well, 1 kilometer per hour for 2 hours, travel a kilometer in the first hour, kilometer in the second hour, 2 kilometers. Or, this area is 1 kilometer per hour times 2 hours. I have hours divided by hours, which just gives me 1. 1 kilometer times 2 is 2 kilometers. So these are useful things to keep in mind. We can go back and forth between position and velocity. We just need to be very careful to know if we're reading a position graph or a velocity graph. Now, you may be wondering one more thing. You may be wondering many things, actually, at this point. If you're wondering many things and it's not the thing that I'm about to, draw arrows to, pause the video, take a second, double check the book, but we're going to press ahead. We're going to ask, what if the velocity isn't constant? So now we've been talking about this, and we've been using constant velocity, linear motion, it's the textbook's very kind of clunky way of saying this, constant velocity, linear motion, as a model to describe the motion of objects. So even when I was walking in class, we talked about me having a constant velocity, even when we saw it wasn't exactly constant. And so this has worked very well for us, but it's a very small subset of everything. So what if it's not constant? What if it's changing? So you might ask, what does this look like? Well, this is a position. I'm sorry, I got briefly interrupted there. I have no recollection of what I was saying, but I'm assuming it was something about the fact if we have a changing velocity, what does this graph even look like? It's going to look something like this. So you might wonder, how do I know that this is a changing velocity? Well, let's zoom in. Right now, if I were to look at this, it looks kind of like a straight line over here, right? Straightish. And so this has a small slope. Small slope, small velocity, right? Because the velocity is the slope. But if I look at it later on, up here, this is looking pretty straightish up here. But now we have a big slope. A large slope, perhaps, which means a large velocity. So this is the easiest way to tell that the velocity is changing. If we zoom in and look, down here it looks kind of flattish. Up here it looks kind of steepish. So the velocity is in fact changing. Now, let's get a little bit of talk before we get too into this. We want to be able to talk about the average velocity. The average velocity is the total displacement, good old-fashioned delta x there, divided by the total time. This is the velocity we had been talking about before. When there's only one velocity, it is the average velocity. Up here, the average velocity for this whole thing would start here and here, and it would be the slope of this line, because that's my delta x from start to finish, my delta t from start to finish. You'll notice it's not quite my initial velocity. It's a little faster than that. It's not quite my final velocity. It's a little slower than that. It's somewhere in the middle. It's an average, more or less. Now, the instantaneous velocity is the velocity at some particular moment of the motion. Those were those two velocities, for example, that I had drawn before. The velocity at the beginning was a slow velocity. We were still approximating it, but we were getting close. And the velocity at the end was a large velocity, a fast velocity. And then we have one new idea, this idea of acceleration, which is the rate of change of velocity, which sounds a lot like the rate of change of position that we had before. And in fact, if I were to look at a velocity time curve, this is one that is changing, right? I'm starting at a small velocity, ending at a large velocity. So this could be the velocity curve for a position curve as we saw before. I might say that this is starting at rest, so v naught, or v at time 0, is equal to 0 meters per second. T naught is equal to 0 seconds. This is often why we call things v naught, but not always. Naught means at the beginning. Let's say up here at the end, it is going 10 meters per second at some time 5 seconds. I could then ask, what is the acceleration? What is the rate of change of velocity? So acceleration would be delta v over delta t, just like velocity was delta x over delta t, the rate of change of position. And so just in the same kind of manner, this will be my change in velocity, my final velocity minus my initial velocity, divided by my final time minus my initial time, or 10 meters per second divided by 5 seconds, which feels a little clunky, but a meter per second divided by a second means I get another second on the bottom there. So this is 10 meters per second squared, because it is 10 meters per second, and I got 2 seconds there on the bottom. All right. So it's a positive 10 meters per second squared because I'm speeding up, going from a 0 velocity to a positive velocity. Meters per second squared because those meters per second squared are my units of acceleration. And acceleration, still a vector because I care if it's positive or negative. All right, this is going to carry us through sections 1.4, the rest of it in 1.5. I think it might be tiny bit into 1.6 talking about acceleration, or not entirely. So this is really just getting used to this terminology. We're going to start doing full-on problems with accelerated motion, but for now, we really kind of are going to stick towards a little bit of just acceleration and a little bit of constant velocity.